Hi, everyone. Can you hear us on the call? Um, Hope you can. We're going to get started here shortly. Nick, are we asking everyone to submit their AIA number on the
I
call?
have, if they put their AIA number in when they registered, I'm tracking it.
Okay. If you didn't hear that, we're tracking attendance if you put your AIA number when you registered. Otherwise, feel free to put it in the chat and we'll count attendance. And for those of us here, give it to Nick. All right, welcome everyone. This is session 3 of our AIA 2030 commitment series, focusing on breaking boundaries with embodied carbon. This is being hosted by the AIA Colorado Committee on the Environment, and Mead and Hunt has so generously provided food and drinks for us tonight. Thank you. Tiffany and I are the co-chairs of the COTE committee this year, and we'll be guiding you through this presentation for the first part, and then we'll introduce our speakers and have them talk about their case study. We have Renee Azerbegi with us. She is the National Decarbonization and Sustainability Leader at Mead and Hunt, and John Kramer, who is the Building Performance Team Leader at Mead and Hunt. And they'll be going through a case study that'll talk about operational and embodied carbon. This year, we have been focusing on the 2030 commitment because of that focus for operational and embodied carbon. Joining the commitment is a thing that we are trying to push all Colorado firms to join. Even though we're right here at 2024, almost to 25, it's not too late to join the commitment. Start submitting project information and data to the system so we can start to track how the industry is performing as a whole. The 2030 commitment was started as a 2030 challenge, and then AIA took it on as a formal commitment. And it has a tiered reduction from 60% reduction in 2010, down 10% every 5 years, to carbon neutral in 2030. So starting in 2025, there's a goal of 90% reduction. The big point of the challenge, though, is really this DDX network that takes all of the information of projects from the firms and starts to track where they are in their journey towards zero operational carbon. The first step is to sign the commitment letter. Then you create a sustainability action plan. And there are so many resources out there from firms who have signed on to build your own sustainability action plan. Within that action plan, you lay out how you want to meet your 2030 targets, and then you report all of the projects in the DDX. And then every 3 years, you will review and update your SAP. There's a lot of information out there on what goes into an SAP. And so if you are thinking of starting this, definitely look into all of the resources available online, and it to help you prep for that. If you haven't joined, it kind of talks about your firm operations and how you plan to implement this in your firm to try to meet the 2030 commitment. So here are the different steps: company commitment, design and approach, goal setting and evaluation, governance and reporting, internal training and education, which is a critical piece, outreach, advocacy, and external knowledge sharing, and then operations and outlook. A lot of people think it might be too daunting to jump in, but really, if you are doing an energy model or embodied carbon calculations on your projects, you have the information you need to input. It's basic project data and performance information. They say it takes about 30 minutes to input it. They also have a bulk input process for much larger firms as well. The DDX is an online platform that was created to track all of these. So you can see kind of small clip here of what type of information they're asking, and they will create a baseline EUI for you and tell you based off of the 2030 commitment what target you should be trying to hit for this project, and give you what your target should be and what your predicted EUI is based off of the information that you've input already into the DDX. Today, again, we'll talk about operational and embodied carbon, but we wanted to give a little primer on embodied carbon for those that might not be as familiar with it. Embodied carbon refers to greenhouse gases emitted during the manufacture, transportation, construction, maintenance, and disposal of materials used to construct a building. And that's in comparison to operational carbon, which really focuses on the energy that a building needs and consumes during its operation. Some common abbreviations you might see throughout the presentation: global warming potential, which is calculated in kilograms of CO2 equivalency per meter squared, or in some instances per square foot. Operational embodied emissions, GHG are greenhouse gases. LCA is a life cycle analysis. This is how we calculate the global warming potential of a project, the total emissions. A whole building life cycle analysis has the WB ahead of the LCA. EPD is an environmental product declaration, and that is something that you will receive from the manufacturers that talks about the manufacturing process and breaks down what emissions are made during the manufacturing of a product. Global warming potential is how we calculate it as a carbon footprint, and everything is compared to carbon dioxide. So even though the emissions might not directly be carbon dioxide, it is calculated and compared to the equivalency of CO2 to have a baseline for all calculations of this. It's important because when we look at kind of the total global impacts of emissions, we have building operations, building materials and construction, transportation industry, and other, and we see that the built environment is almost 40%. So as architects, engineers, and anyone participating in construction of buildings in the built environment, we have quite a bit of say in how we can reduce this. As we're doing a life cycle analysis, we look at different life cycle stages. A1 through A3 and A4 is the raw material extraction all the way to it being delivered on site. That's cradle to gate, and we tend to see most of the project's emissions happen in this early phase. The rest is the use phase: maintenance, repair, replace, end of life. How are we going to be taking this apart and then disposing of it through Module D: reuse, recycling, and energy recovery. This is a sample chart from one of the projects that we worked with KLNA to calculate the global warming potential for a project. And it just goes to illustrate kind of how those the global warming potential is spread across those different phases. So I'll hand it over to our presenters now. They're going to go through a case study of the Appleton Airport.
Thanks, Marcel.
Yeah, get that.
Thanks.
So Sean and I are going to talk about how much carbon is too much carbon, and just kind of give a comparative perspective on total carbon as it relates to a building, not just in year one, but the whole life of a building. We talked about that. So a little bit about Mean Hunt. We are an engineering and architecture firm. Architecture is primarily focused on small aviation as well as DoD. And then construction is kind of interesting. It's focused on renewable natural gas development and waste heat recovery design and installation. We're number 84 in top green design firms, founded, 120 plus years ago. And we've signed on to the AIA 2030. Was that like in a few years ago? And also we've signed on to the SE 2050, which is an embodied carbon commitment by the structural engineers, because we have structural engineers in-house as well. So we're basically a medium-sized firm. We're about 1,400 people. Some of the projects we're excited about are the net zeros and the LEED platinums and LEED gold as well. The first project on the top right here is actually before we joined Hunt. It was the first first net zero airport project in the country. And it's a small airport at Appleton. Now we're doing this case studies on another Appleton airport project that we're gonna show you. And then Contra Costa County net zero and Denver water. You probably heard about that one. Net zero and LEED platinum, and that was a good one too. So what are we doing about carbon for our company? First, we signed onto the AIA 2030 commitment. This is just over the past few years. I got to lead actually the first corporate ESG report, basically. And that is the first step of, actually they were calculating their carbon before this. They had an environmental sustainability plan a few years before that they were tracking for years. But this incorporates the sustainability, the social side, the environmental side, all into one. And then the next year, 2024, we were excited because it actually became like the business plan as well. So it's the whole foundation of what we do. And I wanted to point out this one number. I didn't write it down, but you have to remember it. 6,500. That is metric tons of carbon that our company emits every year. So that would, at least last year, that's how much it was, 6,500. So we're going to show you another number at the end, just to kind of give a relative scale of what that means. And then in 2030, so those are goals now. Now we're at the SC 2030 goals of 40% and 70% embodied carbon reduction for the SC 2050 challenge. We're evaluating MEP 2040. We'll talk about refrigerants today as well and what that entails in that. We're actually going to calculate the refrigerant impact as well, because MEP 2040 is focused on that. And now John is going to show how we're actually doing for the 2030 challenge.
Yeah, thanks. So we've been working on multiple projects that we're documenting recording for AIA 2030. So we have about 16 from 2021, 9 from 2022, and then 7, 23, and 8 in 2024. And they're all somewhere between 250,000 and 500,000 square foot total for those years. And what we're seeing is we're on track to meet our goal of AIA 2030 or get close to that. We're currently seeing about 55 to 57% reduction in energy use intensity. So that's kind of the energy per square foot annually. And our goal is about 80% to carbon neutral, kind of knowing that our building types that we work on are going to be a little more challenging than some others, just because we do a lot of airports and commercial and some industrial. So we have 100% of our projects reporting embodied carbon, 100% are doing net zero energy gap analysis. So even if they're not doing a net zero project, we'll at least show them what it would take to get there so they can think about that in the future and they have that reported. And then we're also doing 62% are solar ready. So this, I'll just clear off the screen. Are y'all seeing that message up top on your screen?
No, not.
Okay. And here's a chart of how we're on track. So we're seeing a trend towards reaching the AIA 2030 goal. And currently we're seeing over 50% reduction in our target of 80% to 90%, and eventually carbon neutral is on track, and we're feeling optimistic about that.
So if we could take out the airport process loads, we'd definitely be there.
Yeah, we'll have another slide where we talk more about that. But yeah, airports are very intensive on all types of process loads that you don't see in a typical office building. So here we see more computers and printers, whatever you plug into a wall. Airports are actually plugging airplanes into basically exterior outlets and charging them, or powering, air conditioning, all that stuff. So airports are a very challenging building type. Yeah, so we start talking about carbon, and then we break it out in these three different areas, and we have embodied carbon, of course, and then operational carbon, which is sort of what my team specializes in: energy modeling, setting energy targets, reducing energy, increasing energy efficiency, renewable energy, and everything. But we thought we'd pause for a second and talk about what is a metric ton of CO2, because ultimately all that energy gets converted into some metric of CO2 equivalent that we have to wrap our heads around. Just energy is very abstract. A metric ton of CO2 is kind of abstract as well. So it's roughly the size or the volume of a two-story house. It's about 27 feet cubed. And I'm an engineer, so I have to throw in all the disclaimers. That's at like atmospheric altitude and pressure and certain temperatures and all that stuff. But roughly that's how you can envision it. It is a metric ton. So if you know a ton of bricks or whatever weighs a ton, like your Subaru Outback is 2 tons or whatever. But as far as volume goes, it's hard to visualize. So that's important because we want people to be able to visualize, say, when we're talking about 6,500 CO2 metric tons, and then you're offsetting that, you kind of have an idea of like, well, what's the equivalent of houses that you just offset? Yep. So our designs have an impact. So we want to make sure that we're accounting for not just one thing and looking into like just operational carbon or just embodied carbon. We want to think about all the intersections of those. That's really important, and it takes analysis that gets into discussions with the design team. Things can't be met prescriptively, so you do have to model performance and do analysis that is complex, and there's not always a rule of thumb that's going to be the same and repeatable for every project. So it's another thing to keep into account, and another abstract thing that you have to be able to explain to design teams and clients. So these are the three big players. Definitely talked a lot about operational carbons. I feel like the last 20 years, that's kind of been the trend. People just love talking about energy and energy models and energy efficiency, and that's already in code. You can do performance requirements to meet the code requirements, and that lately embodied carbons become much more important because people have started to quantify and document how much carbon goes into just building all the materials that go into a building. And then we're going to talk about refrigerant, because that's currently a lot of, I guess you can call mandates and treaties and protocols around the world. So, there's like the Paris Accord, the Tokyo Accord. Now there's the COTE agreement that has been ratified in the US, and we're phasing out refrigerants that have too high of a global warming potential. We're trying to find replacements for them. It's kind of another really big piece of the puzzle. Cool. So I'll cover some key concepts. Some of these I don't think we covered earlier. So energy use intensity. We have energy on a unit basis. It's just a metric, so you can compare different buildings that are different sizes, maybe within a similar building type. So you're just talking about the energy per square foot on an annual basis. And it's helpful for benchmarking, kind of knowing what's out there, what are other buildings doing, what target and goal should I set for my building. Or a metric, how is my building performing compared to a stock of similar building types. So when we talk about airports, for instance, an EUI can range quite a bit, but then we can narrow it down. Instead of a typical airport, which maybe have big airports, small airports, and everything in between, an EUI can be anywhere from 80 up to 500. So then we gradually compartmentalize that a little bit. So you have small hub airports or mid hub airports, and then the EUI becomes a better comparison metric. And then global warming potential, we covered already. I'll keep going. And then we get to embodied carbon, and I'll hand it to Renee.
So in a typical design, about 75% of a project is basically the structure. So the foundation's structural frame, floor decks, roof decks, etc. And the materials, about 95% of that, or sorry, 90% of that, over 90% is concrete, steel, insulation, and aluminum. So that's kind of typical, but it depends. This is commercial. If you're doing residential, it's gonna look a lot different because of the wood, there's a lot more wood, and things like that. So it just depends on the building type, really, and what the overall structural system is. We'd like to use wood to reduce embodied carbon regularly as much as we can, on commercial projects. Marisol went through this a little bit. This is a diagram that kind of shows what is involved with how much energy goes into the A1, A3 materials versus transport, replacement, waste disposal, waste transit. But so you can quantify like what time in the building's life you're going to have these impacts. So the first year of operation, you're going to have the A1 through A5, actually it goes A5 impacts. And then throughout the life of the building, you're going to have B4 through B5 impacts because you're replacing materials as they wear out. And then at the end of the life of the building, then you get to the C category. One thing that's good to keep in mind is that embodied carbon policies are being developed across the entire country. And this is a map that's always in flux. It's from the Carbon Leadership Forum, which is a great website for embodied carbon resources. And you can see that some of these are planned or they're already adopted, which is the blue. Red is planned, blue is regulatory already. And light blue is, there's an incentive as well. I'm trying to figure out where that incentive is coming from. There's an incentive in Colorado for embodied carbon. It's probably in Denver. But yeah, so you definitely want to see if you're working in lots of different states, which we do, we work nationwide, like what policies you have to meet already. And this is a really good tool to figure out what the current policy is. Back to you, John.
Yeah, so back to operational carbon, the last couple of decades, we've seen roughly this method, which is saying you have your building, either existing or it's new. You're going to start with a code min building, and then you're going to focus on efficiency. So you kind of go from that top bar down to reducing the energy, reducing your EY. And now the next step is electrify the building, because the more you electrify, the more you can offset that energy used by the building with renewable energy. Whereas if you're using natural gas, you can't really offset that. So this has been kind of the standard method for basically decarbonizing when you start talking about operational carbon and reducing energy, electrify, add renewable energy. So that gets you to a low enough EY, or essentially your energy usage, which would be, I don't know if y'all can see the mouse, but that bottom part of the graph. And then that means less renewable energy you have to basically pay for to offset your energy usage and get to carbon neutral. And it's again kind of just looking at the operational side, and we're going to talk about how that is related and not necessarily in the way you would expect with embodied carbon or even refrigerants. So these are your traditional energy efficiency measures. In almost any project, you probably go through a list of these, and you can look at your advanced energy design guide, or it might be an IECC or ASH rate, just your prescriptive requirements, and tells you increase insulation. That's great. Reduce your lighting power density, daylighting, occupancy sensors, LEDs, and then you start looking at your super expensive, high efficiency HVAC, so heat pumps, geothermal. It can be whatever has energy recovery, and then maybe optimize controls and set points. So again, that's just looking at the energy part of it. And then when you add in the embodied carbon, then it, oh wow, everything gets so much more complex because they don't necessarily align. So when you, for instance, improve just from the energy perspective, you know, your operational carbon of adding insulation, that insulation might be really bad from an embodied carbon perspective. So now you have to optimize whatever insulation you're doing. From an embodied carbon perspective, you might think, well, let's just do something that's very low on the embodied carbon side, such as bad insulation or mineral wool. And then on the operational carbon side, maybe you want to use continuous insulation, spray foam, something that's kind of bad for embodied carbon, so it has a very high carbon impact. So to optimize that, you do the analysis, energy models, as well as your embodied carbon, your whole building LCA. So you can use software where you quantify the amount of embodied carbon that goes into a building. It takes into account all the insulation, other stuff as well. But mostly it's steel, concrete, and insulation with some of the three big players for embodied carbon. And then as far as how that translates to your energy consumption, then you can start comparing the two. Refrigerant heavy HVAC is another area where energy modelers and building performance people like me don't bat an eye recommending VRF, for instance, which has a ton of refrigerants in it, or maybe some type of heat pump system. But then when you start thinking about the embodied carbon of all that refrigerant, then maybe you have to reconsider it, as well as maybe some other, as we'll see, some of the modern refrigerant types are becoming less carbon intensive, but there's still some amount of global warming potential associated with those. And they're also got other things that code's going to start mandating, like they might be hazardous from a flammability or some other standpoint. So we want to optimize operational embodied carbon as much as we can and not just look at one in kind of a silo or without looking at the other. So low global warming potential refrigerants, they're starting to be rolled out, they're starting to be mandated. The COTE Accord has been adopted, and most of the big players are already producing, the big players of who manufacture refrigerants, such as Trane and Daikin and all the other manufacturers out there. They're starting to make things that kind of transition away from, huge 14,000 whatever global warming potential to something under 1,000. So they're transitioning to something better. Yep. So you want to, again, electrify your building because that allows you to offset it with renewable energy. Some of the major players are still HVAC and your service hot water, the things that are, depending on the building type, going to use up more energy than, say, your lighting or your exterior lighting, your plug loads and all that. And then all electric heating generally is going to be a good thing. Some climates it's going to be so cold that heat pumps maybe currently it's hard to find good ones that work, but they are out there. So you can find heat pumps that will operate in sub-zero temperatures. That's usually a major pushback. People, when you start getting ASHRAE climate zone 5 or 6 or higher, people want to argue that they need natural gas to heat their building. It's not necessarily true. There's plenty of projects that are doing some type of heat pump, geothermal, something else that's much more efficient and all electric. Then on-site renewable energy to offset the energy usage. And Renee is going to talk more about refrigerants.
Yeah, you heard a little bit about it from John already, so I won't go belabor it too much. Yeah, we banned R12, so that's good because that was like 10,000 or more. But in 2025, all new refrigerants are going to have to be R32 to R454B. But you can see it was R410A was kind of the standard after R22. Still kind of a lot of global warming potential. But it's going to take a long time to get rid of the R22 that we already have, the R410A, like a really long time. So these refrigerants are going to be in our system for a long time. And you know what else? They leak. They leak a lot. I mean, this is standard language from the US Clean Air Act, that it's okay for, you only have to do something about it if your commercial refrigeration doesn't exceed 20%, or depending on the pounds, doesn't exceed, again, 20% to 30%, 10% for comfort cooling, but I think those are for smaller systems. So that means say, if it's 20%, every 5 years, you're completely having to replace your refrigerant. And so it's kind of like one of those things you don't really think about, but it adds up. And we'll show you how it adds up in this case study. So we'll go into the Appleton Airport case study.
Yeah, so we did energy modeling on the Appleton Airport concourse expansion. So it's an existing airport that you kind of see in the background. And then that part closest to us, all the way back to where it starts to curve, is an expansion. Really beautiful project, great design. There will be new PV on the roof on that kind of slope side that you see closest to us. And there is actually a pretty big existing PV array over here, about 0.5 megawatt, I think. So pretty sizable PV array. And they're real interested in adding more PV, which is great. And then you can see roughly, it might change from that image, but somewhere around, I don't know, 6 to 10 additional gates added to the project. I think currently it's at 6. So one of the measures we looked at for improving the energy efficiency of it, and we almost didn't even have to recommend it. The client seemed like they wanted to do it. So we're like, great. Geo-exchange, also known as kind of a geofield or geothermal with heat recovery chillers. So that optimizes your condenser loop to where you're just using ground temperatures to basically reject heat to or extract heat from, depending on if you're heating or cooling. And then heat recovery chillers are nice because they're all electric. They couple well with geo-exchange loops, and they can simultaneously heat and cool. So while you're heating, say, the interior building where there's generally going to be a high people load and they're putting off enough heat that you're always in cooling at some part of the year in that building, you can extract heat from that refrigerant of that heat recovery chiller and use it to heat, say, the perimeter of the building. So it's a great efficiency measure. You're basically taking something that would have been wasted and you're recovering it and using it for the building and lowering your energy use intensity, or EY. So it's a really great efficiency measure. And then chilled beams with energy recovery ventilation, those are not super common. There are some, I've seen one up in Broomfield. There's actually a school they renovated and it worked really well to put these big chilled beams on the roof. And they're kind of a efficient way of conditioning a space. It's a little different than what we're normally used to, but it's a high efficiency way of basically sucking up warm air naturally and then letting cold air drop down to the ground. So you're saving a lot on fan energy by using it. And coupling that with energy recovery ventilation, that brings the ventilation air, the fresh oxygen basically to the space, while also again extracting waste heat or waste energy and using it to potentially preheat the outdoor airstream coming in. So it's another really great energy saving measure. And then I mentioned they have a lot of solar PV on the roof. They're still getting grant funding on that, but currently it's over 0.5 megawatt, so pretty sizable for rooftop PV array. And then the HVAC is all electric. I think the only gas on the project might be from the existing, and then potentially for the concessions. I'm not sure if they've nailed down exactly what the concessions are. Last I looked, it's actually just a beer garden, so I don't think there'll be any natural gas there, but that might change in the future. And then the envelope, this is a climate zone 6A in ASHRAE, so it's up in Wisconsin, in Appleton, so it's cold climate, kind of humid as well. They do get some amount of hot days in the summer, but primarily it's cold, heating dominated climate, so that the envelope is well above what's prescribed by Wisconsin building code. So they went above and beyond on that. Really great performing windows, roof insulation, all that. And for the concourse expansion, the EUI that we modeled was about 87 kBTU per square foot per year. And that's beating your peers. Basically, they'd have an EUI about, I don't know, over 100, somewhere around 100 and 120. So they're exceeding that by a pretty good percentage. And that's without PV. When you add PV in, the EUI drops down to about 75. So really great performing concourse expansion. I don't know if y'all can see all this, but so the top two tables we traditionally have done for most of our clients. And the top one, it puts energy in terms of dollars. And we're just comparing different energy efficiency measures. In this case, these are two HVAC options that the first one is what you would typically see. It's like the status quo. It's what they had at the existing. And then we're showing our second option, the chilled beam, the dedicated outdoor air system with energy recovery, and the geo-exchange loop and heat recovery chillers and all that. And so we start putting it in dollars, which is a very tangible thing. People can kind of wrap their head around it. And so we get a first cost, the annual energy cost. And then we did a life cycle cost analysis over 30 years to see roughly what the payback would be and what the net present value was. So we can present information about those efficiency measures so that when someone says, well, why would we do a geothermal loop? It's so expensive. We can say, we're going to save this much more money per year or however you want to word it. And then you're
This was actually cheaper.
Yeah,
Yeah.
the first cost was cheaper too, as well as the operational cost. And then that second table in orange, we're talking about energy, which is where we get a lot of the numbers for carbon and emissions from. So we're talking about EOI, and this was early analysis. So that EOI is a little bit different, less than 1% of where we were a second ago, but we're using that to compare the energy usage to that traditional system. So a VAV with just your typical natural gas boiler and whatever chiller and all that would have an EOI of 88.2, whereas the chilled beam with energy recovery would be a little lower at 86. So then we'd start converting things to emissions and start talking about metric tons of CO2, quantify it. Annual greenhouse gas emission savings, about 38.9 metric tons of CO2. So we can start putting it in those numbers, and we're trying to educate the clients, but also show them something that should be as tangible as dollars. So it's always coming back. People think in terms of dollars still because energy and carbon is very abstract. So we say 38.9 metric tons of CO2 equivalent you save. And then we say that's equivalent of 1.9 garbage trucks of waste recycled instead of to a landfill. You can put it in terms of taxi cabs driving per year, or whatever analogy you want to use to represent that carbon. And then equivalent home energy use for 1 year, that's about 4.9. Cars off the road per year, 8.4. And then we added the bottom table, the one in purple, the social aspect of it, because we don't want to just, again, think in terms of isolation, not just dollars or even energy or carbon, but there is a social player in here. And in this case, it was used to kind of rank these different systems. So we have passenger comfort being a very important component of an airport. It's kind of the equivalent of occupant comfort in the building. Like, why would you pick this if it's to make your occupants really cold and uncomfortable? You're going to pick something that they're going to enjoy being in that space. So we ranked that. Acoustics, innovation, future flexibility, some other ones as well. Electrification potential we had in there. First cost, operational cost, embodied carbon, be refrigerant. So there's a lot of different ways you could rank it. Back to the energy model. So we have our end use breakdown. So that pie chart shows what we're talking about earlier. In green, we have both our interior equipment and our exterior equipment, which at an airport, those are quite a bit larger than your typical building. Typically, those would probably be, I don't know, under 25%, but in an airport, just because you have your TSA equipment, your baggage handling equipment, a lot of x-rays, you're plugging planes in to charge them or to power while they're cleaning them or to condition them. And maybe you have a jet bridge, the air conditioning. So there's this huge interior and exterior load. So those are making up together over half of the total energy usage. And then you see all the other end uses, just like in red or heating and blue or cooling, are relatively low compared to that. And that's important because, again, at airports, you can reduce most of these things. Exterior equipment is still kind of a hard puzzle. Can you electrify that? Can you come up with an energy efficient version of that? So that's something we've been working on a lot. And again, we got the EOI down to about 87 from our latest models, and the building is being constructed right now. So we'll hopefully in the next couple of years have some measured data we can compare that with. And so then the refrigerants, that is a rendering of inside the building. I think that's the beer garden you can see over there. And then this is where the hold rooms would be. The refrigerants for the heat recovery chiller are R410A, which is a little bit better on the global warming potential than its predecessor, basically. So it's like what I consider a transition, as different manufacturers have to adopt new codes and they can't use things that had ozone depletion or high global warming potential. So now they're coming up with things, and eventually, hopefully, it gets even better. So R410A is where the market currently is. And heat recovery chillers use a ton of refrigerant. So 500 pounds is a lot. Typical home air conditioner is probably under 3 pounds, unless you have a giant house. But for like a 2,000 or 3,000 square foot house, and you're air conditioning it, about 3 to 5 pounds maybe of refrigerant. That is a lot of refrigerant. Here's kind of a graphic of what the heat recovery chiller might look like, and roughly, it's like a heat pump, so the compressors are running all the time, so the life expectancy is about 20 years. And that's important because you include that in your life cycle cost analysis, but also your whole building LCA, and when you're tracking the embodied carbon, because whenever you install the machine, you put the refrigerant in, it leaks a certain amount, it leaks some annually as it's just operating. And then when you basically replace it, you can't salvage a lot of that refrigerant, so a lot of it gets lost. So we have about 1% loss during installation. Predicting how much is lost annually, the numbers we found from EPA is about 15% annually, which is higher than you would expect, but if you've ever refilled the refrigerant at your house, it's probably more than that. I had to replace my house twice in the last few years, and I have no idea why. So I had to fill it with 3 pounds of refrigerant. And from some of our commercial and industrial clients, the same thing we've heard is they'll have a leak. It's really hard to detect. So they have to go just put more in. Instead of figuring out where that leak was, they just keep putting more refrigerant in. Not the ideal scenario. So this refrigerant is got a global warming potential of over 2,000 kilograms of CO2 equivalent. Not very good. I think eventually R410A is currently, they're replacing it with like R32 or something that's quite a bit better. So it's like under 500, I think. And then I'll hand it back over to Renee.
So we looked at a lot of different options to reduce embodied carbon. The biggest, I guess, embodied carbon move is the CLT deck, replacing steel deck on the roof or on the ceiling. And then the project also has exterior walls with brick and metal panel cladding and polyiso cyanurate board insulation. So when we look at, hard to read, but wall insulation types, looking at mineral wall versus the polyiso on the roof, different levels, different amounts of mineral wall and different amounts of roof. We found a combination that kind of uses the least, which is the one that's the 2198 option 2, which has 6 inches of mineral wool and 13 inches of mineral wool on the roof. Now, has anybody ever done mineral wool on a roof? Yeah, okay. So it's considered lower embodied carbon, but you probably need, a more of it to get the same insulation levels as you would with polyiso, because our value per inch isn't as high. But it's ended up being the lowest embodied carbon wise. And then if you look at it from a kilograms of CO2 per meter squared perspective, kind of similar results. Option 2 is showing the best. Just for reference, the International Living Futures Institute zero carbon requirement, if you're trying to have a low embodied carbon building, is does not exceed 500 kilograms, and we're at 609 with this option. So we're close, but I'm sure that this was developed for an office building, not for an airport building. It's just slightly different. And we weren't pursuing that, but it's just like there's not very many metrics on this to even compare to. So we compared it to that one. And this is carbon over time for 50 years. So if you look at operational carbon in the dark blue, you can see, you have your first year operational carbon, and then it's going down because emissions are the grid is getting cleaner. So your emissions, your operational carbon goes down over time. And your embodied carbon, a big hit is the first year, but then you have to replace stuff. So here's, after 20 years, after 40 years, you have to replace parts of the building. So that would be your embodied carbon. Your refrigerant carbon is always leaking. So, and then you have to replace the system at the end of its useful life. So when you look at it in totality, operational carbon, embodied carbon is clearly, the most significant impact you have in the first year. But the operational carbon adds up over time. But refrigerant carbon is the surprise, right? Like that's a lot of refrigerant carbon that people aren't really tracking. And if you look at it from a percentage perspective, embodied carbon is 81%, then it goes down to 22 because the refrigerants go up in the operational price up as well. So that is, oh, and so what does that mean? So the total amount of carbon over 50 years was 17,600 metric tons, or about 6% of the population in Denver annual residential energy use in 1 year, just for this small airport project. Now remember that number, 6,500? That was for our company. And think about how many building projects there are in that you're working on and what their carbon impact might be. So your work is going to be the bigger thing that you do. I mean, it's still important to be as green as possible as a company, but your work is going to have way more of an impact. So we want you to think about all of those things when you're designing your buildings, all three: operational, carbon, and refrigerant. And thank you. That's all I have. You guys, do you have any questions for us?
So if you extend the life of the building, it only gets better. I mean, you really need to focus on the systems, I guess. Because you're
Yeah.
sitting in a building that's what, 100 years?
Yeah.
So the brick building isn't that big a deal.
Mhm. Right. And, you know, we were debating, do we use 60 years? Do we use 40 years? Do we use 50 years for this analysis? And, you know, I've worked on a lot of buildings in Denver where they were demoed after 30 or 40 years and built with brand new net zero LEED platinums on top. It's like, that doesn't feel right, but okay. You know, so what is the normal life? This is historic, so that's why it's so old, you know, which is great. The historic thing really does protect buildings, and that does a designation. But if you're not historic, how long do your buildings last? And how long before people say, oh, we don't like that one. It's got too much work to redo it. You know, CU Boulder is a really good example of a campus that reuses a lot of their buildings. So is GSA, their Denver Federal Center. They reuse a lot of their buildings locally. And so if we can try to reuse more of our buildings, obviously that would be the biggest move we can do.
And then the other things, I mean, when you did that airport, talk about obviously the structural system, you talk about TLT, you know, substituting concrete or steel or whatever. And then we talk about insulation and envelope, but a lot of our buildings still have a lot of glass. I mean, was there some effort put into maybe reducing the glass, just the quantity of glass, because that's such a poor performer in
Yeah.
the overall picture, and to find that balance again, especially in an airport where it's nice to sit there and look at all the planes and the landscape beyond and all that, but how much conversation was had in that regard.
It's a conversation that comes up.
Yeah. What was the the client reaction? How strong, or is it getting more attention? Because it's
we're finding like
value of
it's
that
a
glass
budget issue often because
sure.
you know, like some of our jobs, they reduce the glass. It starts really lofty with lots of glass, and then after the budget's refined, there's the glass that needs to be there and not as much excessive glass. But airports tend to have a lot of glass on the first floor, on the top, the concourse level, and a lot less on the bottom level. And so that's how they meet code, because they average the two, you know what I mean? But we definitely work with them. We also do daylight analysis so that we can make sure that the people aren't sitting and needing sunglasses, because sometimes that happens. When you're inside at an airport, there's that much glass. So we don't want that to happen. We worked on the Denver concourse expansions, a couple of them, and there's a lot of glass there. We try to get them to do electrochromic, but they didn't listen.
Heating and cooling, I mean, like Appleton, that was in a predominant heating environment, so it's maybe that's an issue with lots of glass, but pretty warm too.
Yeah. We try to get them to lower the window to wall ratio, is what we call it. So under, I guess, the code requirements, if they're going to meet the prescriptive path, usually they go over that and then end up doing an energy model for them to meet the performance path. And that's roughly around like 30 or 40%, depending on what code they're on, of windows to wall. And that conversation, you know, there's just a lot of players, and there's a lot of other drivers behind that decision. So it's aesthetics, and you kind of think of it from occupant comfort, even though we found there's a lot of glare from windows. But yeah, just to meet code compliance becomes to be tricky because some you have small glass building in some areas, and that's wasting energy. It's adding cost, and it looks pretty though, especially from the outside. That I think that's the big driver is from outside the building. You have these beautiful, maybe fritted glass and these nice patterns on it and different colors, and it matches the aesthetic of what the owner wants.
Yeah, but frit doesn't really help as much. It's just a good performing glass. Mhm.
So did you discuss triple glazing or in that environment, maybe even the noise aspect of that or noise reduction aspect?
Yeah,
I
I
think
don't know. We looked at that for this one.
I think we did like triple pane and then thermally broken and argon fills and all the premium products out there. Maybe I think airports generally have to be metal framed, so they can't do fiberglass or whatever the premium products are, just because of all the vibrations and how heavy duty they have to be. Usually, cost drives it out, so they probably would love to do it, but then they see the price tag for triple pane glazing, and we have 50 or 60% window to wall ratio. It adds up pretty fast, so then they stick with maybe double pane, but a better thermally broken frame around it or whatever they can do to improve that double pane.
We do have some projects, airport projects included that are doing electrochromic, like Fort Wayne Airport. And they're going to get they're trying to figure out how to get the tax credit. There's a big tax credit, with the Inflation Reduction Act for electrochromic. So we're working with them to figure out how they can make sure they capture it. But it's like expiring, I think, next year. Hopefully it'll come back to as something else. But yeah, there's a lot of, they don't make it easy to get these tax incentives. But
already expiring.
well, the electrochromic one specifically, it might not be expiring, might be changing form, but something's going to change in January. Mhm.
It's so interesting to see you all talk about refrigerants included in this, because when we do embodied carbon calculations, we typically will focus on the envelope or the structure, maybe interiors, but MEP seems to be that one area that nobody really wants to touch yet. And so I'm curious for those of us who are trying to gather this information to understand the impact of the MEP systems. Do you have any suggestions for how we might start to approximate that in our projects?
Yeah, the MEP 2040 is a good tool.
Okay.
Yeah. And also, I was looking at embodied carbon before it became a thing, but you could get a lead pilot credit for embodied carbon, but no one was really like paying attention. And then it became a lead point, and you could get a whole bunch of points, and all of a sudden it was a thing. So like, I know that LEED has had the refrigerant credit for a long time, but it's only worth 1 point and it doesn't move the needle. It's like you just check it or you don't. But they could certainly change their language so that people pay attention to this and do more about it. In my opinion.
Focusing so much on concrete and steel and
Yeah.
the typical building material.
Right.
Insulation.
I mean, starting next year in 2025, that's when those new refrigerants are going to come online. So the brand new buildings after that will be okay. But we have, again, all this huge existing stock, and it's going to be a while before that goes away.
That's policy's driving that a lot more than the code and building rating systems and everything. So once you have federal mandate saying you have to phase these out, all the manufacturers have to listen, and then it doesn't, like, whoever is specifying your MEP and your mechanical plans, they don't really have a choice at that point. They have to pick the refrigerant that fits that system that's available when they're going to procure it, and policy is going to drive that. So luckily that has been ratified and it's rolling out here pretty soon. So that'll help transition away from some of the really bad R410As and some of the other ones with really high global warming finishes.
That's why the passive stuff is so important. You can improve your envelope. It has like if you can reduce your system sizes.
Yeah.
I wanted to see if anybody online had any questions. And if you do, if you could please put them in the chat, that would be.
I put a
Great.
note in there.
Oh, okay.
Haven't seen any
Okay.
come through yet.
All right. Cool.
Do you think that codes. So European, German codes, for example, it's been forever that they just basically mandate the performance of a building. So this many kilowatt hours per square foot per year is what you're allowed to use maximum.
I love that.
So then you just, you know, then you're just, well, talking to my, I mean, they're basically at the point now where you can't really do a single family home anymore without a heat pump. You typically end up with triple glazing, new construction.
Mhm.
I mean, this is the most recent. So
Mhm.
wondering whether there's any discussion ongoing here. Where people think about that, because we have this good prescriptive here, right? And we're like, okay, this much insulation, I mean,
Yeah.
you know, ratios don't matter. And at the end, we will analyze the building performance against the building that is designed to meet minimums, code minimums, right? And then we will say, oh, we're going to be this percentage point better. But it's never, I mean, you're showing the data here, okay, this is how much it's going to use per year.
Mhm.
KBT.
Per year, yeah, which is essentially.
Yeah.
similar thing,
Same thing,
just different.
Well, I think like operationally, we're not there yet. Denver is experimenting with us with EUI targets, which is exciting, but very kind of frustrating too, because we should have run it past more people. Maybe QC did a little bit better. But so that's kind of an EUI target. But until we can figure out how to have a policy about embodied carbon that's numeric and quantifiable and in our codes, people are going to keep demolishing buildings. And, you know, so that's what we need is something to help us protect our existing building stock and make people reuse buildings. Yeah, that's yeah, yeah.
Any more questions? And we can continue the conversation as well afterwards.
I guess outside of, this client
Thanks,
is great,
Krista.
right? Because they wanted to pursue these metrics and this reduction. But if you have that, if you have a client that's motivated, what are you seeing as like the biggest hurdle then to really reaching those targets? Is like industry still behind, manufacturers still behind?
For which
The
kind of
budget
targets?
thing.
Which kind of targets are we
I
talking
think
about?
just overall like carbon reduction. I know the refrigerant thing, I feel like is a whole other beast, and we have like states like California that's completely doing away with like 410A, right? So then how do you even deal with that the project, right? And so, but just like overall, I think maybe operational and embodied carbon reduction, if you have someone that's driven to do that, what's one of the biggest hurdles to really achieving that bigger picture?
Any thoughts on that, John?
And there's some products out there that we used on this building, and the architects liked it because it helped with the code requirements and everything. So I think it's like Greenger, which had a really good kind of insulation property to it, and it looked good too. So they're picking things that were available, but it was also kind of like to me it was a new product. I hadn't really heard of it, and we had to do a lot of research and figure out a lot of the information, the data sets behind it to analyze it. So that was one of the challenges of going with this new super efficient, envelope product.
Sometimes they don't have EPDs, it's going for lead and you need EPD and they don't have it. You're like, please, please, please go get one.
Right. Well, and I feel
You know.
like if your project's not pursuing timber, then it's like, we're just never gonna get it. And then it's a lost cause, right? Like,
Yeah.
it's like the go-to,
Yeah.
which is great, but like at our campus, we can't use any wood. We just can't.
Oh,
And so our new projects wanted to do timber and reduce embodied carbon and really reach that metric.
mhm. Yeah.
Fire marshal won't go for it. So it's like on any situation, I know timber is better from a crime protection standpoint, but yeah, someone's like, well,
Yeah.
I guess we're not gonna.
Yeah.
So
I mean, fire codes,
yeah.
the fire marshals can be a hindrance a lot of times. for a lot of different reasons. When you think about
Yes.
natural ventilation and things like that.
Yeah.
But we still like to have the conversations and start that out that way. Yeah, I mean, whatever hurdles we come across, we just try to work with people to get over them, you know?
I think it's all about like education.
Yeah,
Just having the dialogue.
yeah, I mean, wood is a huge embodied carbon helper, you know? So it's hard, like we're looking, FAA requirements, we have to deal with a lot of that at airport world, which means where's your solar panels facing? Are they giving any glare to the air traffic controllers? Can you put carbon cure in the apron level? Are they gonna allow that? You know, like, so we have a lot of unique
A lot of regulations.
regulations and things.
It's not a typology that I would think would be really pushing it as much as they
No,
seem to be, so, which is great, but we need, you know.
yeah,
You gotta offset all that external.
yeah,
I think sourcing is also a big player as well. Where the project is located, what is available from a concrete perspective, because that's so impactful. Steel, Nucor has some carbon neutral steel, where the energy created is offset by hydropower, or some other renewables, but there's a premium on top of that as well. So whether your clients are willing to pay, and embodied carbon is something that is very hard to convince clients of if it's not in policy, because they don't feel it directly in the moment.
we can use more policy language to help with embodied carbon for sure. I just saw the National Western Center, Stockyards and Event Center, they had a nice reuse of the pens and the barns in terms of wood into the building. Reuse of materials and salvage materials also really good.
And I wanted to give a big thanks to our COTE committee and our COTE committee members who are here, and all year long, all the input that we've received as well. Wanted to give a quick plug for 2025 and our speaker series, and then we're gonna have the call for volunteers soon. So we hope all of you will continue on with us, and we'll look at doing a speaker series in the spring so that we're not competing with a lot of different conferences and events that are happening, tend to happen later in the fall. So keep an eye out for the call for volunteers.
Thank you. Thanks, everyone.
Nice to meet you in person.